In 2022, the James Webb Space Telescope photographed galaxies formed when the universe was 2% of its current age, massive enough to break every model of how the cosmos assembles itself. We believed the early universe was dark and slow. It was not. It was violent, fast, and impossibly efficient. Tonight we witness black holes outweighing their own galaxies, oxygen detected in a galaxy born 290 million years after the Big Bang, and a cosmological crisis with no answer yet. If that sounds worth witnessing, like and subscribe. We begin now. On the morning of December 25th, 2021, a rocket lifted off from the Guiana Space Center in French Guiana, carrying what may be the single most complex object humanity has ever sent beyond Earth's atmosphere. The James Webb Space Telescope weighed roughly 6,500 kilograms, barely more than half the mass of the Hubble Space Telescope it was built to succeed. But the comparison to Hubble, though unavoidable, fundamentally misleads. These two instruments were not different versions of the same machine. They were designed to answer different questions, using different physics, to look at different parts of the universe's history. The difference begins with the mirror. The James Webb Space Telescope carries a primary mirror 6.5 meters across, built from 18 hexagonal segments coated in gold, each weighing roughly 20 kilograms. Hubble's primary mirror measures 2.5 meters. The area matters more than the diameter. The new telescope collects roughly 5.5 times as much light per second. But more critical than size is what kind of light it was built to receive. Hubble was engineered to see in ultraviolet through near-infrared wavelengths. The James Webb Space Telescope sees in infrared from just below what human eyes can detect out to wavelengths 28.5 times longer than the reddest light we can see. This shift in sensitivity is the entire story. The universe holds objects that Hubble was physically incapable of observing, and the James Webb Space Telescope was built specifically to see them. The launch itself was, by any honest measure, frightening. To fit inside the Ariane 5 rocket, the telescope had to be folded. The primary mirror folded, the secondary mirror folded. A 5-layer thermal shield the size of a tennis court folded into a package small enough to fit inside the rocket fairing. The shield's purpose is to keep the telescope's instruments at negative 223 degrees Celsius, cold enough to detect the faint infrared glow of the first galaxies without the thermal noise of the telescope's own components overwhelming the signal. The heat it was designed to block radiates from 3 sources: Earth, the Moon, and the star at the center of our solar system. After launch, the telescope spent roughly 30 days unfolding itself in space. Engineers at the Space Telescope Science Institute in Baltimore had identified 344 single points of failure in that sequence, meaning 344 individual steps, where a single mechanical failure would have ended the mission permanently. There is no repair mission for a spacecraft parked nearly 1 million miles from Earth at the gravitational balance point between our planet and the star it orbits, the location called Lagrange Point 2. Hubble, positioned only about 340 miles above Earth, was visited by astronauts 5 times for repairs and upgrades. The James Webb Space Telescope was sent somewhere fundamentally unreachable. If it failed, it would simply remain there, drifting, operational for nothing. It did not fail. Every one of those 344 steps executed correctly. The mirror segments aligned to a precision smaller than a wavelength of light. The instruments cooled. By mid-2022, science operations had begun, and within weeks the telescope was sending back data that the people who built it described as better than their most optimistic projections. The operative question, then, was what it would find when pointed at the oldest light in the universe, the infrared glow of the very first galaxies, which had been traveling toward Earth for nearly 13 billion years, invisible until this moment. That question was about to be answered in ways no one had fully prepared for. Light from distant galaxies carries information about where it began. As the universe expands, that light is stretched. A photon that started its journey as visible light, emitted by a young star in a galaxy forming at the edge of observable space, will arrive at Earth as infrared radiation. The farther the source, the older the light, the more expansion has stretched it, and the deeper into the infrared it shifts. Astronomers call this process redshift, and it is not a metaphor or an approximation, but a direct physical consequence of the fact that space itself has grown since the light departed. When Hubble stared at the sky for days at a time to produce its iconic deep field images, it was collecting light from galaxies that formed 1 to 3 billion years after the Big Bang. Beyond that distance, the light fell outside its detection range. The first galaxies to form after the universe cooled enough to allow atoms to exist were born somewhere between 100 and 400 million years after the Big Bang. Their light has been traveling toward Earth ever since. Some of it is arriving right now, every second, carrying information about objects that predate our solar system by 9 billion years or more. But it arrives as infrared radiation, and for most of modern astronomical history, it arrived undetected. Hubble simply could not see it. No optical or near-infrared instrument on the ground or in orbit could. The universe had been warm, and the warmest objects in our neighborhood. Ground-based telescopes face the additional problem of Earth's atmosphere, which absorbs most infrared wavelengths before they reach any instrument on the surface. The only solution was an instrument cold enough, large enough, and positioned far enough above the atmosphere to receive the signal directly. The cosmic period the telescope was built to observe has a name in the field: the Epoch of Reionization. It refers to the era when the very first stars and galaxies ignited, and their ultraviolet radiation ionized the neutral hydrogen fog that had filled the universe since recombination. Before this epoch, the universe was opaque to most forms of light. Photons could not travel freely. Then, within the first billion years, the first sources of radiation turned on and began burning through that fog, and the universe became transparent. The James Webb Space Telescope was engineered to see across that transition and back into the darkness before it, to detect the faint infrared glow of the earliest structures at the moment they first emerged. When Stefano Carniani at the Scuola Normale Superiore in Pisa and his collaborators began analyzing the telescope's first deep exposures, they were looking at photons that had left their sources when the universe was less than 5% of its current age. What those photons contained, what they revealed about the objects that emitted them, was already contradicting the models before the first full year of science operations was complete. The first scientific deep field image from the James Webb Space Telescope was released on July 11, 2022. The target was a galaxy cluster called SMACS 0723, located about 5.12 billion light-years from Earth. A galaxy cluster at that distance was not the primary subject, it was a tool. Galaxy clusters contained so much mass, concentrated in such a dense region, that their gravity bends light traveling around them, a phenomenon called gravitational lensing. Objects that would normally be too faint and too distant to detect directly become visible when a foreground cluster magnifies and distorts the light coming from behind it. The telescope was using the cluster as a natural lens, a cosmic magnifier capable of reaching deeper than any instrument could reach on its own. The image showed what happens when you combine that lens with a mirror 6.5 meters wide and detectors sensitive enough to see objects 100 times fainter than Hubble could detect. The patch of sky covered was equivalent to what you would see holding a grain of sand at arm's length against a dark sky. Inside that grain were thousands of galaxies. Some appeared as smears and arcs, their shapes warped by the gravitational field of the foreground cluster bending their light around it. Some glowed reddish, their light stretched into the infrared by billions of years of travel. Many had never been seen before. The oldest among them had emitted the light captured in that image, when the universe was less than 1 billion years old. What made the reaction from researchers unusual was not just the content of the image, but its context. This was a commissioning image, released to demonstrate that the telescope was functional and performing at specification. The SMACS 0723 field was selected in part because it had been previously observed by Hubble, allowing direct before and after comparison. Galaxies that Hubble had spent 11 days capturing as faint smudges at the edge of its detection limit appeared in the new telescope's exposure with visible structure, spiral arms, bright cores, color gradients indicating different stellar populations and ages. The new instrument acquired equivalent depth in a fraction of that exposure time, with sensitivity still substantially above what Hubble could have reached in extended observation. The scientific community's response was immediate. Researchers posted comparisons on public forums within hours. Several noted that the redshift of the faintest visible objects indicated they were being seen at epochs beyond what Hubble had routinely confirmed. One astronomer described the experience as equivalent to putting on glasses for the first time, except the glasses were showing things that had been theoretically expected to exist but never directly observed. The practical implication was that the telescope was performing at or above its design specifications. In its first weeks of operation, before its dedicated science programs had even formally begun, what the data already contained, quietly, was a warning. The galaxies in that image were not all where the prevailing models expected them to be in brightness, in size, in apparent mass, or in apparent age. Some of them looked different from what the leading frameworks of galaxy formation predicted they should look like at those distances. The SMACS field was a preview. The deep programs, the ones specifically designed to stare at the oldest and faintest objects in the sky for hundreds of hours at a time, had not yet begun pointing at the universe. The James Webb Space Telescope Advanced Deep Extragalactic Survey, known as JWST, was designed before the telescope launched and represented the most ambitious attempt to systematically map the earliest galaxies ever proposed. The program was led by Daniel Eisenstein at the Harvard and Smithsonian Center for Astrophysics and brought together researchers from across multiple institutions, including Kevin Hainline at the University of Arizona, Brant Robertson at the University of California, Santa Cruz, and Ben Johnson at the Center for Astrophysics. The survey targeted two fields in the southern sky, the Goods North and Goods South fields, the same regions that Hubble had stared at for days, and in some cases weeks, to produce the deepest images of the distant universe ever captured with that instrument. The decision to overlap with Hubble's fields was deliberate. Every galaxy Hubble had detected there would serve as a calibration point, and everything beyond Hubble's detection limit would be new territory. The scale of improvement is worth sitting with for a moment. Hubble spent roughly 400 orbits, over 11 days of cumulative integration time, capturing the Hubble Ultra Deep Field, an image that showed galaxies at distances corresponding to roughly 500 to 800 million years after the Big Bang. Those galaxies appeared as faint smudges, their spectra nearly impossible to measure, their redshifts estimated from color alone rather than direct measurement. The James Webb Space Telescope could obtain equivalent depth in a fraction of that time and had the additional capability of taking spectra, measuring precise redshifts and chemical compositions of hundreds of objects simultaneously using its near-infrared spectrograph. The difference was not incremental. It was the difference between hearing that a sound existed in a distant room and being able to identify every individual voice. The first major spectroscopic results from JWST were published in January 2023 in the journal Nature Astronomy. A team led by Emma Curtis Lake at the University of Hertfordshire provided spectroscopic confirmation of 4 galaxies at redshifts between 10.3 and 13.2, corresponding to a period when the universe was between 300 and 450 million years old. These were direct measurements of the specific wavelengths of known emission lines, shifted by known amounts, confirming beyond any methodological ambiguity where in the universe's history these objects existed. At the time of publication, they were the most distant spectroscopically confirmed galaxies ever recorded. The numbers in those spectra carried an implication that team members were careful about stating too directly in the initial announcement. The galaxies appeared to contain more stars, more total stellar mass, than models of galaxy formation in the early universe predicted should be there. They were not faint smudges at the edge of the theoretically expected distribution. They were, in several cases, bright and structured, suggesting substantial stellar populations that had been building for longer than the models allowed. A galaxy at redshift 13 requires that its stars began forming within the first few 100 million years after the Big Bang. Under the standard model of cosmic structure formation, that process should have been slower, more gradual, beginning with small concentrations of dark matter that only gradually accumulated enough gas to form stars in significant numbers. The data was saying something different. Larger, statistically robust datasets were needed before firm claims could be made. But the direction of the discrepancy from the very first confirmed detections was already pointing the same way every time. The standard model of cosmic structure formation, called lambda cold dark matter, had been refined over roughly 4 decades through observations, simulations, and mathematical analysis. It describes a universe that began with small quantum fluctuations in density, which gravity amplified over hundreds of millions of years into the first structures, which collapsed under their own weight into the first dark matter halos, which then accumulated gas, which cooled and fragmented into the first stars. The process was described as hierarchical, meaning small things formed first, and larger structures assembled gradually by merging with other small things. This model had been tested against a remarkable range of observations: the cosmic microwave background radiation, the distribution of galaxies in the nearby universe, the clustering statistics of surveys containing millions of objects. In nearly every test, it performed well. Cosmologists had considerable confidence in it. The James Webb Space Telescope's first year of observations introduced a problem. Across multiple survey programs, the data consistently showed galaxies at redshifts above 10 that were brighter and more massive than the model predicted they should be. The Cosmic Evolution Early Release Science Survey, led by Stephen Finkelstein at the University of Texas at Austin, catalogued what appeared to be hundreds of candidate galaxies from the first 650 million years of cosmic history. The statistical surplus was not subtle. Luminous galaxies at redshifts above 10 appeared roughly 10 times more common than standard model predictions. Caitlin Casey at the University of California, Santa Barbara, co-leading the Cosmos Webb survey, addressed this directly. Cosmos Webb was mapping the largest area of sky yet attempted with the telescope, ultimately cataloguing roughly 800,000 galaxies, spanning 98% of cosmic history. As the data accumulated, Casey noted publicly what many researchers were observing privately. The telescope was delivering results that were persistently at odds with what the models said should be there. Since the telescope turned on, she observed, astronomers had been wondering whether the datasets were breaking the cosmological model. The question researchers were trying not to ask too loudly was whether the model itself was fundamentally wrong. There were conservative alternatives. Perhaps the measurements of stellar mass were systematically overestimated, because the light from actively accreting black holes was being mistaken for starlight. Perhaps galaxy formation in the early universe was unusually intense, with brief, concentrated episodes of star formation that made galaxies appear more massive than their average histories would predict. Both explanations were technically possible. Neither had strong independent support. Both were being proposed specifically to rescue the model from data that otherwise contradicted it. The problem with the conservative interpretations was not that they were implausible, but that they required the early universe to operate in ways that were themselves unexplained. Concentrated star formation at the required intensity had no established physical mechanism. Widespread misidentification of black hole light as stellar light required those black holes to be present in enormous numbers at extremely early times, which introduced a separate crisis about how they got there. Resolving one anomaly created another. Every patch opened a new seam, and the seams were all running in the same direction. Among the results that forced cosmologists to articulate the problem more formally was a paper published in Nature in February 2023. Ivo Labbé at Swinburne University in Melbourne led a team that analyzed data from the Cosmic Evolution Early Release Science Survey and identified 6 galaxies formed within the first 500 to 700 million years after the Big Bang, each estimated to contain between 10 billion and 100 billion times the mass of a typical star. For context, the Milky Way is considered a moderately large galaxy and contains roughly 60 billion such masses in stars. These 6 objects, formed when the universe was less than 5% of its current age, were comparable in stellar mass to some of the largest galaxies in the present-day universe. The problem was not the observation itself, but what it required to be true under the standard model. Lambda, cold dark matter, describes galaxy formation as a process that begins with dark matter halos, regions where dark matter was slightly denser than average, which grow by gravitational attraction, pulling in gas that cools and eventually forms stars. The rate at which this process can convert raw gas into stars is constrained by known physics. Typical galaxies across cosmic history convert somewhere between 5 and 10% of their available gas into stars over their lifetimes. To assemble 10 billion to 100 billion stellar masses in stars within 500 million years. Starting from the Big Bang, these galaxies would need to have converted close to 100% of every available atom of gas into stars, at a rate sustained without interruption from the very beginning. That efficiency is not merely unusual. Under known physics of star formation and the feedback processes by which young stars and black holes heat and expel surrounding gas, it is essentially impossible. Mike Boylan-Kolchin at the University of Texas at Austin, who had spent years developing theoretical predictions for early galaxy populations, was direct about the implications. In a companion paper published in Nature Astronomy the same year, he stated that if the mass estimates were correct, the observations placed the standard model under severe tension, using precise statistical language that in cosmological research signifies a crisis rather than a minor adjustment. Erica Nelson at the University of Colorado, Boulder, described the objects as absolutely wild, adding that they implied either an early universe more chaotic and efficient than any model had assumed, or a universe in which the physical processes governing star formation operated under rules that had not yet been identified. Later, spectroscopic follow-up in 2024 introduced some qualifications. A portion of the apparent stellar mass in some candidates appeared to come from actively accreting black holes rather than stars, meaning the stellar mass estimates had been somewhat inflated. Guoqiao Sun at Northwestern University and collaborators proposed that unusually intense episodes of star formation could explain a fraction of the excess. These revisions did not resolve the crisis. They reduced its magnitude. Even after correction, the population of massive galaxies at redshifts above 10 remained roughly 10 times larger than standard predictions. The objects Labbé's team had found became known informally as the universe breakers, and the name proved more accurate than hyperbole typically does. On May 30th, 2024, a team of researchers, including Stefano Carniani, Brant Robertson, Kevin Hainline, and Ben Johnson, announced the spectroscopic confirmation of the most distant galaxy ever directly measured. The object, designated JWST 14-0 in the survey catalogue, had a confirmed redshift of 14.32. That number corresponds to a specific moment in the universe's history, 290 million years after the Big Bang. The light recorded by the James Webb Space Telescope had left this galaxy when the universe was roughly 2% of its current age, predating our own solar system by more than 9 billion years. The object was not a faint smudge at the detection limit. It measured over 1,600 light-years across and contained hundreds of millions of times the mass of a typical star in stars alone. Robertson stated at the time of announcement that the team could have detected this galaxy even if it were 10 times fainter than it appeared, suggesting that similar or larger objects might be awaiting detection even deeper in time, possibly into the first 200 million years. after the Big Bang. The confirmation of this galaxy as a bright, structured, massive object at such extreme distance was remarkable on its own. Then came the follow-up. In March 2025, combined observations from the James Webb Space Telescope and the Atacama Large Millimeter Array, the radio telescope network in Chile, detected a specific chemical signature in this galaxy: oxygen. The detection of oxygen in any object in the distant universe carries an implication that is not subtle and cannot be explained away. Oxygen is the third most abundant element in the universe overall, but it is not primordial. The Big Bang produced primarily hydrogen and helium, with trace amounts of lithium. Every atom of oxygen in the universe was forged inside a star, released when that star died, either by shedding its outer layers at the end of its life or by exploding as a supernova. For oxygen to be present in a galaxy, that galaxy must have already hosted entire generations of stars that lived out their full lifespans and died. The timeline this requires is extraordinary. Massive stars, the kind that explode as supernovae and enrich their surroundings with oxygen and heavier elements, live for roughly a few million to a few tens of millions of years. But before they could exist in JWST 14.0, the first generation of stars had to form, and those stars had to live and die, enriching the surrounding gas before a second generation took shape. All of this had to occur within the first 290 million years of the universe's existence, because the James Webb Space Telescope measured the chemical signature at that epoch. Under the models that existed before this telescope, the year 290 million after the Big Bang was barely beyond the expected start of star formation itself. The very first stars were predicted to begin forming somewhere around 100 to 200 million years after the Big Bang, meaning the entire chain from first ignition to multiple stellar generations, to oxygen-enriched gas, to a fully assembled galaxy with hundreds of millions of stellar masses had been compressed into an interval the models described as barely enough time for the process to begin. Robertson called the finding completely unanticipated. The word accurately describes the scale of revision it demanded. The impossibility arriving in parallel with the early galaxy mass crisis came from a different class of object entirely. Black holes at the centers of galaxies, the supermassive variety with masses ranging from millions to billions of times that of a typical star, are not rare in the present-day universe. The Milky Way hosts one at its center, known as Sagittarius A star, with a mass of roughly 4 million stellar masses. The most massive galaxy clusters harbor central black holes exceeding 10 billion stellar masses. Their presence is so standard that astronomers routinely include a central black hole in the modeling of any large galaxy's dynamics. The problem the James Webb Space Telescope introduced was chronological. Growing a black hole from a stellar seed, the kind that forms when a massive star collapses at the end of its life, to supermassive scale requires time. The physics governing that growth has a ceiling, called the Eddington limit, which describes the maximum rate at which a black hole can accrete surrounding matter before radiation pressure from the infalling gas blows away its own fuel supply. Sustained Eddington limited growth over hundreds of millions of years represents the fastest physically understood pathway to supermassive scale. Even at that maximum rate, assembling a black hole of 100 million or 1 billion stellar masses from a stellar seed takes a time measured in the hundreds of millions of years, requiring near-perfect conditions from the earliest moments of star formation. The telescope was finding them earlier than that. Roberto Maiolino at Cambridge University and collaborators published results in Nature in 2024, confirming the presence of a black hole at the center of a galaxy called GNZ11, situated at a redshift of 10.6, corresponding to roughly 400 million years after the Big Bang. The black hole's mass was estimated at 1.6 million stellar masses, accreting roughly 1 stellar mass of material every 5 years. A separate detection using combined data from the Chandra X-ray Observatory and the James Webb Space Telescope identified a black hole of 10 million to 100 million stellar masses at a redshift corresponding to about 450 million years after the Big Bang. The deeper crisis came from a class of objects the telescope began cataloguing in large numbers, which acquired the informal name little red dots. Jorrit Matthey at IST Austria and colleagues characterized them systematically in 2024. They appeared compact, with spectral energy distributions shaped like a letter V. Their central black hole masses ranged from 1 million to 100 million stellar masses. In the present-day universe, the mass of a central black hole typically represents about 0.1% of the total stellar mass of its host galaxy. In the little red dots, that ratio ran to 30% or higher, a factor of 300 times the locally observed relationship. The black holes in these objects did not merely outpace the model, they appeared to dominate their host galaxies in a way that current theoretical frameworks had no mechanism to produce. Matthey stated directly nowhere nearby. The data was real, its interpretation was the problem. The first proposed explanation invoked a mechanism called direct collapse. In the standard model, black holes form from the remnants of dead stars. A star 20 times the mass of a typical star lives for roughly 10 million years, then collapses. Its remnant core may form a black hole of several stellar masses. Growing from there to 1 million or 1 billion stellar masses through accretion takes time, but there was a theoretical alternative. Under specific conditions in the early universe, a massive cloud of primordial gas could collapse directly into a black hole without passing through a stellar phase at all. These direct collapse black holes would be born with masses of 10,000 to 100,000 stellar masses, giving them a significant head start over stellar remnants. The conditions required for this process were plausible in the dense, radiation-filled environment of the early universe, but they were also quite specific. Producing them in the numbers required to explain 341 catalogued objects stretched the mechanism considerably. The second explanation required black holes to grow faster than the Eddington limit allows. Super-Eddington accretion is not impossible. Simulations show that under certain configurations of surrounding gas, a black hole can temporarily exceed the Eddington rate by factors of several. But the little red dots appeared to require sustained growth at these elevated rates over hundreds of millions of years, under conditions that would need to remain favorable across timescales vastly exceeding any simulated episode. The energy output of a black hole accreting at 10 or 20 times the Eddington rate would also produce enough radiation to destroy the surrounding galaxy. Yet these objects showed evidence of concurrent star formation. The mechanisms required to allow one process while permitting the other were not identified. A third possibility had fewer advocates, but was harder to dismiss. It invoked primordial black holes, objects that formed directly from density fluctuations in the very early universe, within the first seconds after the Big Bang, long before any star existed. Primordial black holes had been theorized for decades and had been proposed as a candidate for at least some fraction of dark matter. If they existed in sufficient numbers and masses, they would provide seeds far more massive than any stellar remnant could supply. The challenge was that no direct observational evidence for primordial black holes had been established, and the conditions required to produce them in the required abundance were not well constrained by existing theory. What Matthey and colleagues had identified was a systematic challenge to the account of how the universe built its first structures. The little red dots were 10 to 100 times more abundant than expected. Each hosted a central engine that outweighed its own galaxy by ratios observed nowhere in the local universe. The people studying them said, with the precision that scientific language affords, that they could not explain what they were looking at. The mystery had become a crisis of understanding. By the end of 2024, a pattern had emerged from the accumulating data that individual results had only partially suggested. The James Webb Space Telescope had been operational for roughly 2.5 years, and across multiple independent survey programs, targeting different regions of the sky at different wavelengths, the findings were pointing in the same direction. The early universe, the period from roughly 100 to 700 million years after the Big Bang, was not the gradual awakening that the Standard Model described. It was something faster, denser, more chaotic, and more chemically productive than any theoretical framework built before this telescope had anticipated. Consider the constraints the data imposed simultaneously. JWST 14-0 contained oxygen at 290 million years, requiring multiple stellar generations to have lived and died before that moment. The 6 galaxies identified by Ivo Labbé's team at Swinburne contained stellar masses comparable to the Milky Way's at 500 to 700 million years, requiring star formation efficiencies approaching 100% from the very beginning. The little red dots hosted central black holes with masses 30% or more of their total stellar mass, requiring growth rates that exceeded the theoretical speed limit across a population 10 to 100 times larger than any model predicted. Each of these findings, taken alone, was a serious challenge. Together, they implied something more fundamental. The word that appeared most often in researchers' descriptions of the early universe, across papers and conference presentations through 2024 and 2025, was efficiency. The early universe appeared to convert gas into stars, assemble dark matter halos into galaxies, and grow black holes at rates that violated every established understanding of the relevant processes. The question was, why? 3 classes of explanation were offered with varying degrees of theoretical backing. The first held that star formation in the early universe was simply more efficient than it is today, perhaps because the gas was denser or subject to different turbulent conditions that allowed larger fractions to collapse into stars before stellar feedback could disrupt the process. The second held that the Standard Model's description of dark matter was incomplete, and that a different dark matter candidate would produce a different pattern of early structure formation that better matched the observations. The third was the most uncomfortable, that the cosmological model itself contained an error in its treatment of the very early universe, possibly in the period of rapid expansion called inflation, that changed the initial conditions in ways that had not been accounted for. None of these explanations had achieved consensus. All 3 were being actively developed and tested against new data as each observing cycle added to the archive. What was not in dispute by 2025 was the character of the discrepancy. The universe had not assembled itself slowly and patiently from small beginnings. In its first few 100 million years, it had done something that looked, from the vantage point of our much later position in time, like a nearly instantaneous burst of structure, chemistry, and mass. The quiet, dark, gradual dawn that cosmologists had modeled for decades had not happened. Something faster had taken its place, governed by physics the field had not yet identified, operating at efficiencies the field had not thought possible, and the telescope that revealed this was only just beginning its work. The James Webb Space Telescope was not designed only to look backward in time. It was designed to see everything Hubble's instruments had missed, at every distance, in every direction, including the vast structural scaffolding that organizes the universe at its largest scales. When its infrared detectors began mapping the distribution of galaxies across hundreds of millions of light years, what emerged was something that theorists had predicted in broad outline for decades, but had never seen with this clarity. A 3-dimensional web of matter spanning the entire observable universe, organized into filaments, sheets, nodes, and voids on a scale that no human analogy adequately captures. The cosmic web is the largest coherent structure in existence. It formed because the early universe was not perfectly uniform. The quantum fluctuations imprinted at the moment of inflation, tiny variations in density that seeded the formation of everything, were amplified over hundreds of millions of years by gravity. Matter fell along invisible channels defined by dark matter filaments, accumulating where those channels intersected into dense galaxy clusters, while the regions between them were progressively emptied. The result looks in 2-dimensional projections of 3-dimensional survey data. like a foam of interconnected strands with bright nodes at their junctions and vast, dark spaces between them. Galaxies and galaxy clusters crowd the filaments and nodes. The voids between them are almost barren. The filaments themselves are extraordinary objects. A typical dark matter filament connecting two galaxy clusters might span 100 to 300 million light-years in length and contain more mass than thousands of individual galaxies, most of it in dark matter that emits no light. Astronomers cannot image dark matter directly. They map its presence through the behavior of the ordinary matter and galaxies it gravitationally organizes, through gravitational lensing of background light, and through the statistical distribution of galaxies that trace the filament's path through space. R. Brent Tully, at the University of Hawaii, whose team used velocity measurements of tens of thousands of galaxies to map the flow of matter through the local universe, described the result as a system of cosmic watersheds. Just as rivers flow toward valleys, and eventually the sea galaxies flow along channels defined by the dark matter web toward concentrations of mass that function as the ocean basins of the cosmos. What the James Webb Space Telescope added to this picture was depth and resolution in the early universe. Previous surveys had mapped the cosmic web at relatively nearby distances. The telescope's infrared capabilities allowed researchers to trace the large-scale structure back in time, to periods when the web was younger and denser, and to measure with spectroscopic precision the positions and velocities of galaxies along filaments that formed within the first 2 billion years of cosmic history. What they found was that the web's basic architecture was already in place earlier than models had predicted, with substantial galaxy clusters connected by defined filaments at epochs when, according to the standard model, structure formation should still have been in its early phases. The complication that follows from the cosmic web's existence is not abstract. The filaments connect everything. Every galaxy cluster is embedded in a network of dark matter channels that link it to its neighbors, near and distant. Matter flows along these channels continuously, pulled by gravity toward regions of higher density. Individual galaxies are not isolated objects drifting through empty space. They are embedded in a web that exerts influence on their trajectories, their gas supplies, their star formation rates, and their ultimate fates. The Milky Way is embedded in this web, its path through space, its eventual collision with the Andromeda Galaxy, the structure of the local group it belongs to. All of it is shaped by the dark matter filaments threading through our cosmic neighborhood. Understanding our own galaxy requires understanding the web it inhabits, and the web, it turns out, contains regions of a character quite different from the filaments where the galaxies live. The discovery that the universe is organized into a cosmic web implies, as a structural consequence, that the web must have gaps, enormous gaps, regions where the filaments did not form, where matter migrated outward over billions of years toward the surrounding structure, leaving behind a near emptiness so extreme that it defies the intuition shaped by any human experience of space. These regions are called voids. The largest confirmed example of one sits in the direction of the constellation Boötis, in the northern sky, and the numbers required to describe it are worth sitting with before considering what they mean. The Boötis void is approximately 330 million light-years across in its widest dimension. It was discovered in 1981 by Robert Kirshner at Harvard and colleagues during a systematic survey of galaxy redshifts. Their expectation was that galaxies would be distributed with some variation across the survey volume, with filaments and clusters in some places and relative underdensity in others. Instead, they found a region roughly spherical in shape containing essentially nothing, a sphere 330 million light-years in diameter, in a universe where a typical galaxy separation within clusters is measured in millions of light-years, contained approximately 60 galaxies, where models of the large-scale structure predicted thousands should exist. Kirshner reportedly said, after examining the data, that the void was so large he was embarrassed to tell people about it. The Boötis void is vast enough that the entire filamentary cosmic web the structure whose existence the previous chapter traced across hundreds of millions of light-years could be nested inside it with room remaining. It is old enough to have been nearly emptied over the roughly 13 billion years since the Big Bang. Every galaxy that might have populated its interior migrated outward, pulled by the gravitational attraction of the surrounding structure, leaving behind a near vacuum so complete that the dozen or so galaxies now found within it appear to represent a small cluster forming near the void's center rather than a distributed population. The scale has a specific consequence that reshapes the imagination in ways that a list of distances cannot. Consider the following. If our solar system sat at the center of the Boötes void, in precisely the same location it now occupies relative to the nearby universe, astronomers on Earth would not have confirmed the existence of other galaxies until the 1960s. The nearest external galaxies would have been so far beyond the observational technology available to Edwin Hubble in 1925 that the entire conceptual revolution associated with recognizing the universe's vast scale would have been delayed by decades. We would have lived, as an astronomical civilization, inside an expanse of near total emptiness, with no evidence visible through early 20th century instruments that any galaxy beyond our own existed. This is what makes the Boötes void unsettling in a way that extends beyond its physical dimensions. It demonstrates that the universe's distribution of matter is so uneven that your location within it determines your entire picture of reality. The observable universe from inside a deep void and the observable universe from inside a dense filament are empirically different places, even if the underlying physics is identical. And the disturbing possibility the data raises is that our own cosmic neighborhood may not be the dense, typical region we have assumed it to be. The Boötes void is an extreme case, but researchers examining the large-scale structure surrounding our own position in the universe have gradually assembled evidence for something less dramatic but potentially more consequential. We appear to live inside a void ourselves. The structure in question is called the KBC void, named for the researchers who characterized it systematically, Keenan, Barger, and Cowie, in a 2013 paper that initially attracted relatively limited attention. What it describes is an underdense region approximately 2 billion light-years across, centered roughly on our local group, within which the average density of matter is substantially lower than the cosmic mean. 2 billion light-years is a number that requires framing. The Boötes void, the structure described in the previous chapter as so large that discovering it embarrassed its discoverers, is 330 million light-years across. The KBC void is 6 times larger in diameter. It encompasses the Laniakea supercluster, which will be described in detail in the following chapter, the Shapley concentration toward which much of our local universe is gravitationally flowing, and several hundred million light-years of surrounding space in every direction. The local group, the small collection of galaxies including the Milky Way and Andromeda, sits within this underdense region, not at any extreme edge, but roughly within the interior of a structure whose boundaries have been traced through the distribution of thousands of galaxies, measured in multiple independent surveys. The reason this matters beyond simple description of our location is a crisis that has occupied cosmologists for nearly a decade, the Hubble tension. The two most precise methods for measuring the rate at which the universe currently expands produce answers that disagree at a level of statistical significance that should not be possible if both methods are correct. One method uses the early universe, specifically the acoustic oscillations visible in the cosmic microwave background radiation, to infer an expansion rate. The other uses nearby distance ladders, chains of calibrated astronomical measurements, reaching from our own cosmic neighborhood outward to distant galaxies to measure the rate directly. The early universe method yields approximately 67 kilometers per second per megaparsec. The direct local measurement yields approximately 73. The gap between them, expressed in the standard deviations physicists use to evaluate the significance of discrepancies, is 5 to 6. In particle physics, 5 sigma is the threshold for announcing a confirmed discovery. The connection to the KBC void is specific and unresolved. A region of lower than average density experiences different gravitational dynamics than the cosmic mean. Galaxies inside a void tend to be pulled toward its walls, as the void expands and empties over time, a process that imprints an additional outward velocity component on their motions. If our location inside the KBC void introduces a systematic boost to the measured velocities of nearby galaxies, then the local expansion rate measurements might read higher than the true global rate, not because any measurement is wrong in a simple instrumental sense, but because what is being measured locally and what is being calculated from the early universe are genuinely different things. We would be measuring the universe from inside a bubble, and the bubble would be teaching us the wrong number. Whether the KBC void fully accounts for the Hubble tension remains contested. Some analyses suggest the underdensity is not quite pronounced enough to explain the entire 5 to 6 sigma gap. Others find that once the void's influence is properly modeled, the tension shrinks to levels that could reflect remaining systematic errors. What is clear is that our address in the large-scale structure of the universe is not a neutral fact. It is a physical circumstance with measurable consequences for what our instruments tell us about the fundamental constants of cosmology. The void we inhabit has a boundary. Beyond its walls, matter accumulates in the structures that gravity has built over billions of years. And the most immediate of those structures, the one that contains the Milky Way and roughly 100,000 of its galactic neighbors, has a name that was formally established only in 2014. Brent Tully at the University of Hawaii and colleagues published a paper in Nature that year, mapping what they called Laniakea, a Hawaiian word meaning immeasurable heaven. The name was chosen deliberately. The structure it describes had not been recognized as a coherent object before, because the method required to identify it did not exist at sufficient scale until then. Tully's team used a dataset called Cosmic Flows, a catalogue of galaxy distances and velocities assembled over years of careful observation to map the gravitational flows of matter across the local universe. Ordinary surveys of large-scale structure use galaxy positions, where things are. Cosmic flows used galaxy velocities, where things are going, and from those velocities the team reconstructed the gravitational landscape that produces them. Galaxies do not simply sit still between their neighbors. They move, and the direction and speed of that motion traces the underlying mass distribution even where no visible matter is present. By following the velocity field outward in every direction from our position, Tully's team was able to identify the boundaries of the gravitational basin within which our local group resides. The result was a supercluster 500 million light-years across, containing more than 100,000 galaxies and a total mass equivalent to roughly 100 million billion times the mass of a typical star in stars and dark matter combined. The Milky Way and Andromeda sit near its outer edge. The Virgo cluster, the nearest large concentration of galaxies to our local group, sits near its center, and the gravitational flow of the entire supercluster tends inward toward a region in the direction of Centaurus that Tully identified as the primary attractor. Everything in Laniakea is falling, slowly, toward that central concentration, drawn by a gravity well that has been accumulating mass since the early universe. The fact that this structure had gone unmapped as a coherent object until 2014 reveals something important about how difficult the largest scales of the universe are to perceive. Individual galaxies are visible objects. Clusters of galaxies had been mapped for decades, but a supercluster 500 million light-years across, containing 100,000 galaxies in a gravitational basin defined by velocity fields rather than visible boundaries, requires a specific kind of measurement at a specific scale to recognize as a single thing. A subsequent update using the fourth Cosmic Flows catalog, published by Alexandre Dupuy and Hélène Courtois in Astronomy and Astrophysics in 2023, incorporated roughly 56,000 galaxy distance measurements and confirmed the Laniakea volume, while revealing that observed superclusters across the local universe are, on average, an order of magnitude larger than the standard cosmological model predicts they should be. The complication arrives here. Laniakea is already flowing towards something. The entire supercluster, all 500 million light-years of it, all 100,000 galaxies, is moving at roughly 600 kilometers per second toward a concentration of mass in the direction of the Centaurus constellation. What it is moving toward, and what lies beyond it, is the next chapter in understanding how vast the architecture we belong to actually is. Something is pulling, not just our galaxy, not just our local group, not even just our supercluster of 100,000 galaxies. Everything in Laniakea, across 500 million light-years, across distances of several hundred million light-years. The Great Attractor presents a specific observational problem. It lies almost exactly in the plane of the Milky Way galaxy as seen from Earth. Dust and gas in our own galaxy's disk absorb and scatter electromagnetic radiation across much of the spectrum, creating what astronomers call the zone of avoidance, a band across the sky where ground-based and most space-based surveys cannot see clearly. X-ray and radio observations can penetrate this band to some degree, and dedicated surveys have mapped portions of the Norma cluster, a dense concentration of galaxies near the center of the Great Attractor region. But the full extent of the mass distribution responsible for the flows measured across Laniakea remained difficult to characterize directly for decades, because the most powerful tool for mapping it, optical redshift surveys, was precisely what the zone of avoidance prevented. What lies beyond the Great Attractor, visible to surveys that approach from the sides of the zone of avoidance, is the Shapley concentration. George Shapley, the Harvard astronomer who first recognized in the 1930s that the universe extends vastly beyond what had been imagined, discovered this overdensity but could not measure its true extent. Modern surveys have characterized it as the densest concentration of galaxies in the local universe, a region roughly 650 million light-years from our position, containing the mass equivalent of approximately 8,000 typical galaxies, organized into dozens of clusters connected by dense filaments. Its volume is roughly 10 times that of Laniakea. The peculiar velocity flows measured across our local universe suggest that many of the galaxies in our region are ultimately being drawn not just to the Great Attractor, but toward the Shapley concentration behind it, a gravitational sink that has been accumulating mass for billions of years and whose influence extends across a significant fraction of the observable universe. This picture of cosmic flows, superclusters moving toward attractors embedded in larger basins, basins flowing toward even larger concentrations, repeats at successively larger scales until it encounters the cosmic web itself, where the filaments that carry matter toward clusters eventually thin out, and the voids that separate them become the dominant feature. Tully used a watershed analogy. Matter flows along cosmic channels the way water flows down hillsides, and every drop of water, every galaxy, belongs to some basin of attraction that defines where it is heading. We belong to a basin whose ultimate sink may be the Shapley concentration, which itself sits within the larger network of the cosmic web, which is itself distributed unevenly across the observable universe in ways that continue to challenge the models built to describe it. But the flows the telescopes measure, the velocities of those galaxies, produced a number that refused to agree with the number produced by the oldest light in the universe. And that disagreement, which has been growing more precise and more intractable with every passing year, represents what is now the most serious crisis in cosmology. In 2011, Adam Rees at Johns Hopkins University, Saul Perlmutter at the Lawrence Berkeley National Laboratory, and Brian Schmidt at the Australian National University received the Nobel Prize in Physics for discovering that the universe's expansion is accelerating. The discovery, made in 1998 through careful measurements of Type Ia supernovae at different distances, introduced dark energy as the dominant component of the universe, the mysterious force driving galaxies apart at an increasing rate. The measurement that won them the prize required knowing exactly how fast the universe was expanding, a number expressed as the Hubble constant. From that point forward, determining the Hubble constant with precision became one of the central goals of observational cosmology. Adam Rees continued refining the local measurement throughout the 2010s, leading the supernova H0 for the equation of state collaboration. The method uses a chain of calibrated distance measurements, from parallax measurements of nearby stars to pulsating Cepheid variable stars in nearby galaxies, to type Ia supernovae bright enough to be seen across billions of light years. Each rung of this ladder is calibrated against the ones below it, and the total chain stretches from our own galactic neighborhood out to the regime where the pure expansion of the universe dominates over local gravitational motions. By 2022, Rees's team had measured the Hubble constant at 73.17 plus or minus 0.86 kilometers per second per megaparsec. The other value, derived from the cosmic microwave background radiation measured by the Planck satellite and published with the highest precision in 2020, is 67.36 plus or minus 0.54 kilometers per second per megaparsec. The two measurements are both highly precise. They disagree by approximately 6 kilometers per second per megaparsec. Expressed as a statistical significance, the discrepancy stands at 5 to 6 sigma. For decades, the hope was that the disagreement would dissolve once measurement errors were fully characterized and corrected. That hope was directly tested when the James Webb Space Telescope, with its superior sensitivity and resolution, began observing Cepheid variables and supernovae in the same galaxies Rees's team had used with the Hubble Space Telescope. Rees's team published their James Webb Space Telescope calibration results in 2023. The new telescope confirmed the Hubble Space Telescope measurements with high precision. The Hubble constant, measured from the local distance ladder, was 72.6 kilometers per second per megaparsec, matching the Hubble Space Telescope's value of 72.8. Instrumental error had been one of the most plausible explanations for the discrepancy, and the James Webb Space Telescope had now effectively ruled it out. Rees stated directly, "With measurement errors negated, what remains is the real and exciting possibility that we have misunderstood the universe." Wendy Friedman at the University of Chicago, leading an independent team using alternative distance indicators, including the tip of the red giant branch and carbon-rich variable stars, found that 2 of her 3 methods converged on the Planck value and 1 matched Rees. Her interpretation was that a systematic error remained in one of the approaches. Rees, whose method has been refined over more than a decade and scrutinized by multiple independent groups, maintains that the discrepancy is real. The field has no consensus. What it has, confirmed by the most precise telescope ever built, is a genuine, unresolved crisis at the foundation of cosmology. On April 4th, 2024, the Dark Energy Spectroscopic Instrument Collaboration released results from its first year of observations. The instrument, mounted on the male 4-meter telescope at Kitt Peak National Observatory in Arizona, spent that year measuring the redshifts of more than 6 million galaxies, producing the most detailed 3-dimensional map of the large-scale structure of the universe ever assembled. The survey's primary purpose was to measure how the universe's expansion has changed over its history, and specifically to test whether dark energy, the force responsible for that expansion's acceleration, behaves as the simplest models predict. The simplest model is called the cosmological constant. It was introduced by Albert Einstein in 1917 as a term in his equations of general relativity that would counteract gravity and keep the universe static, then discarded when Edwin Hubble discovered the universe was expanding, then restored when Perlmutter, Rees, and Schmidt found the expansion was accelerating. In this model, dark energy has a fixed density at every point in space and at every moment in time. It does not weaken or strengthen as the universe evolves. It is a property of space itself. a constant energy density built into the fabric of reality that pushes outward with exactly the same force regardless of when or where in the universe you measure it. The dark energy spectroscopic instrument data, when combined with measurements from the Planck satellite and supernova surveys, including the Dark Energy Survey, showed something different. The combined analysis produced a deviation from the cosmological constant at a statistical significance of 3.9 sigma, corresponding to confidence that dark energy's behavior has changed over the universe's history. Michael Levi, the director of the Dark Energy Spectroscopic Instrument Project, stated that the data raised the possibility that dark energy had evolved over time. A separate analysis published in Physical Review D in September 2025 by Anwar Jaman Shajib at the University of Chicago and collaborators found that dark energy appeared to have decreased in strength by approximately 10% over recent cosmic history, at a confidence level of 99.6%. This result is extraordinary in its implications. Dark energy is the dominant component of the universe, comprising roughly 68% of all the energy in existence. Ordinary matter, everything that has ever been seen, touched, measured, or modeled in the entire history of science, makes up approximately 5%. If dark energy can change, if the force that determines the ultimate fate of the universe has been evolving throughout cosmic history, then every prediction that depended on its constancy requires revision. The future of the universe, whether it expands forever or eventually reverses, whether the expansion accelerates indefinitely or eventually slows, becomes uncertain in a way it was not before the dark energy spectroscopic instrument results. The theoretical frameworks capable of producing a dynamic dark energy have their own demands. The simplest alternative to the cosmological constant is called a quintessence field, a hypothetical scalar field permeating all of space that slowly evolves over time, weakening or strengthening as the universe ages. Unlike the cosmological constant, which has no physical mechanism and is simply inserted into Einstein's equations as a measured value, quintessence fields arise naturally from certain classes of particle physics, particularly extensions of the Standard Model that include additional scalar degrees of freedom. The challenge is that the quintessence models capable of matching the dark energy spectroscopic instrument data require that this field's evolution be extremely slow and finely tuned, exhibiting no significant variation over the first 10 billion years of cosmic history before shifting measurably in the last few billion. Why a dynamical field would behave as though constant for most of cosmic time and only recently begin evolving is a question none of the existing frameworks answer convincingly. But there is something more specific in the data than a simple weakening, something that the physics of dark energy makes particularly unsettling. The behavior of dark energy is described by a parameter physicists call the equation of state, typically written as the letter W. For the cosmological constant, the simplest model, W equals -1, exactly. Values of W greater than -1 describe dark energy that weakens over time, eventually allowing gravity to potentially reverse the expansion. Values of W less than -1 describe a category with its own name in the literature, phantom energy. Phantom energy grows stronger as the universe expands. The more space there is, the more energy it contains, and the faster it pushes everything apart. The expansion accelerates without limit, and the increasing repulsive force eventually grows strong enough to overcome every other force in nature. Willem Elbers at Durham University and colleagues, analyzing the dark energy spectroscopic instrument data in combination with other surveys, found evidence for something that the standard theoretical frameworks specifically forbid: dark energy whose equation of state crossed the phantom divide. The data suggested that dark energy behaved as phantom energy in the past, with W below -1, but has since weakened and now sits above that threshold. The crossing of this boundary is theoretically problematic, because the simplest models of dark energy, including the cosmological constant, cannot cross it. They sit on one side of the divide and stay there. The data appeared to be describing a universe in which dark energy had done something its simplest descriptions said it could not do. Elbers stated the situation plainly. Dark energy seems to have been phantom in the past, but is no longer phantom today, and the simplest theories do not allow for that kind of behavior. The implication is that dark energy is not a fixed property of space, but something dynamic, something that evolves, whose influence on the universe changes with time. For decades, the standard picture had the universe's future written clearly: expansion forever, accelerating, until every galaxy beyond the local group crosses the cosmic event horizon and the universe grows cold and dark over incomprehensible timescales. That picture required dark energy to remain constant. The dark energy spectroscopic instrument data introduced serious doubt about whether it does. The phantom phase, if real, carries its own terrifying appendix. A universe in which dark energy is phantom does not simply expand forever. It expands at an accelerating rate that increases without bound. Structures that gravity holds together, galaxy clusters, galaxies, star systems, eventually planets, atoms, are progressively torn apart as the expanding repulsive force overwhelms the forces binding them. This outcome has a name: the Big Rip. On the timeline it describes, approximately 2 billion years before the end, the gravitational bonds holding galaxy clusters together are severed. 60 million years before the end, the Milky Way is torn apart. 3 months before the end, our star's planetary system is dismembered. 30 minutes before the end, Earth is pulled into fragments. In the final fraction of a second, atoms themselves are ripped apart. The current data does not confirm that this future is approaching. The evidence suggests dark energy was phantom in the past and has since weakened. But the fact that the dominant component of the universe has already crossed the phantom divide once, that it behaved as a force with no theoretical basis in the standard model for some portion of cosmic history, means the future cannot be read from models that assumed it never would. In September 2025, Henry Tai at Cornell University published a paper in the Journal of Cosmology and Astroparticle Physics that introduced a different kind of ending. Tai's analysis focused on the cosmological constant itself, the value Einstein assigned to the energy of empty space, and proposed that rather than being a fixed positive value driving eternal expansion, it might represent a metastable state. In his model, the effective cosmological constant is not truly constant, but emerges from a landscape of possible vacuum states, and the universe currently occupies one that is slowly evolving. The analysis found that if the constant is negative at the deepest level, the universe's current phase of expansion is temporary. Gravity would eventually win. The timeline Tai's model produces is specific. The universe is currently approximately 13.8 billion years old. His calculation places the total lifespan of the universe at roughly 33 billion years. The current accelerating expansion would continue for approximately 11 more billion years before the gravitational dynamics reversed. From that point, a contraction would begin, slow at first, and then increasingly rapid, until everything collapsed back into a singularity in what cosmologists call the Big Crunch. The end would come approximately 20 billion years from now. For context, the star at the center of our solar system has approximately 5 billion years of hydrogen fusion remaining. Our own solar system would survive into the contracting phase, witness the slowing of the expansion, and eventually be crushed along with every other structure in the universe. Nothing in the known universe would remain outside the final singularity. Young Wook Lee at Yonsei University in South Korea, whose team analyzed the expansion history using supernova data published in 2025, found independent evidence that the universe had already entered a phase of decelerated expansion, consistent with a cosmological constant that is weakening rather than holding steady. The Big Crunch had been the dominant cosmological scenario for much of the 20th century before the 1998 discovery of accelerating expansion appeared to rule it out. Tai's paper and the dark energy spectroscopic instrument results collectively reopened the question. They do not confirm the Big Crunch. They confirm that the answer is not known. The fate of the universe, whether it expands forever, tears itself apart, or collapses back to a singularity, is again genuinely uncertain. 30 years of consensus have dissolved in 2 years of precision measurement. What makes the Big Crunch scenario specifically disorienting is the timeline it sets against familiar reference points. The contraction phase in Ty's model would not begin suddenly or dramatically. It would begin with a subtle deceleration in the expansion rate, a slowing barely detectable at first against the background of normal cosmic motion. Galaxies that have been drifting apart for billions of years would begin drifting apart more slowly, then halt, then begin approaching one another over timescales comparable to the current age of the universe. As the contraction deepened, the cosmic microwave background radiation, the afterglow of the Big Bang that is now cooled to less than 3 degrees above absolute zero and spreads evenly through all of space, would begin to heat up again as the volume of the universe shrank. The sky, dark for trillions of years in every scenario, would grow incrementally brighter as all the energy that had been diluted by expansion began concentrating again. In the final stages of contraction, temperatures would climb to levels where the boundaries between individual galaxy clusters dissolved, then where stars themselves could no longer survive, then where atoms dissociated into their component particles until the singularity. Everything that had ever existed compressed into a point. The 3 possible endings now sit before cosmology with roughly equal scientific standing. The long, cold death of heat entropy measured in years with 100 zeros, the violent dismemberment of every structure in the Big Rip, or the crushing finality of the Big Crunch within a time the universe is already old enough to contemplate. Each is a complete ending. Each operates on scales that dismantle the human capacity for emotional response to numbers, but each is governed by forces that are now revealed to be neither fully understood nor fully stable. Step far enough back from any individual discovery, and a single picture assembles itself. The universe is governed by forces operating at scales and timescales that human civilization has had the tools to measure for, at most, a few decades. Those forces are not stable in the way earlier generations of physicists assumed. They are not fully understood in the way the standard model required, and they are actively determining the fate of everything that exists, including the planet, the civilization, and the instruments that have only just begun to read their behavior. Gravity is the oldest force in cosmological reckoning. It shaped the dark matter into the web described in earlier chapters, pulled the first gas clouds into the first stars, assembled galaxies, clusters, superclusters, and the Laniakea basin within which our local group resides. Gravity governs the flows that pull everything in our local universe toward the great attractor and the Shapley concentration beyond it. On the smallest scales, gravity holds the Earth in its orbit, holds the atmosphere against the surface, holds everything together that the other forces do not bind more tightly. On every scale simultaneously, gravity is the force that organizes, builds, and, given sufficient time and density, destroys. Dark energy is the counterforce. It comprises 68% of everything in the universe, yet it has no physical description beyond a mathematical term in Einstein's equations. Its nature is unknown. Its origin is unknown. Whether it is a property of empty space or a field that evolves through time is, as the dark energy spectroscopic instrument data demonstrated in 2024, now actively contested. It has already behaved in ways the simplest models said it could not, crossing the phantom divide at some point in the universe's past. Its current trajectory, whether it is strengthening, weakening, or holding steady, determines whether the universe ends in heat, death, rip, or crunch, 68% of everything. And we do not know what it is. The Hubble tension sits between them, refusing to resolve. 2 precise measurements of a single quantity, the rate at which the universe expands, made using entirely different physical phenomena across entirely different portions of cosmic history, producing answers that disagree at 5 to 6 sigma. The James Webb Space Telescope confirmed that the disagreement is real and not an artifact of measurement error. The most capable observatory ever built by humanity confirmed that our two most precise methods of reading the universe are telling us contradictory things, and neither can be wrong in a simple, fixable way. Either the early universe model is wrong, or the local universe during these measurements is real and unresolved. We exist inside an active conflict between the universe's fundamental forces, a conflict whose outcome we are only beginning to characterize, using instruments that have been operational for approximately 3 years. What the James Webb Space Telescope revealed in its first chapters was that the early universe was faster, denser, and more chaotic than the models allowed. What it is revealing now, alongside the ground-based instruments that have been transformed by its confirmation of their measurements, is that the universe's fundamental architecture remains in dispute at the level of its most basic parameters. The expansion rate, the nature of dark energy, the ultimate fate of everything, none of these are settled questions, and every new measurement, rather than closing the gap, has been making it larger. The forces at work across those scales leave signatures at every level of the cosmos, including in the trajectories of individual stars. In the spring of 2019, Sergei Koposov at Carnegie Mellon University and the University of Edinburgh was analyzing data from the Southern Stellar Stream spectroscopic survey when he found something that did not belong. A star in the constellation Grus, roughly 29,000 light-years from Earth, was moving at 6 million kilometers per hour. That number is approximately 10 times the velocity of a typical star in our galaxy's disk and represents approximately 0.5% of the speed of light. For reference, the fastest human-made object ever launched, the Parker Solar Probe at its closest approach to our star, reaches roughly 700,000 kilometers per hour. This star was moving 8 times faster. Koposov's team designated it S5 HVS1 and spent the following months reconstructing its trajectory by running its current position and velocity backward through models of the Milky Way's gravitational field. The result was unambiguous. The star had originated near the center of the Milky Way in the dense stellar environment surrounding the supermassive black hole known as Sagittarius A star and had been launched outward approximately 5 million years ago. At that time, anatomically, modern humans did not yet exist. The mechanism responsible is called the Hills mechanism, first proposed theoretically by Jack Hills in 1988. If a binary star system passes close enough to a supermassive black hole, the tidal forces of the black hole can disrupt the pair, capturing one star into a tight orbit while flinging the other away at extreme velocity. The ejected star carries the orbital energy of the original binary, amplified by the immense gravity of the central black hole. The result is a star moving fast enough to escape the galaxy entirely. S5 HVS1 is precisely that object. Its trajectory carries it not into some other part of the Milky Way, but out of the galaxy altogether. It is unbound, meaning the Milky Way's gravity is insufficient to reverse its motion. It will continue accelerating outward through our galactic halo, past the outskirts of the stellar population, and eventually into the intergalactic void between galaxy clusters. There, it will drift for billions of years before its internal fusion exhausts itself, and it dies as a white dwarf, cooling slowly toward absolute zero in a region of space containing no other stars within millions of light-years. Ting Li, then at Carnegie Observatories, and Princeton, who led the broader spectroscopic survey that captured S5 HVS1, described it as a visitor from a strange land. Alex G., also at Carnegie, articulated the star's biography more precisely. Born near a supermassive black hole with many stellar neighbors, it will leave the galaxy and die entirely alone, in the middle of nowhere. The contrast between origin and destination is a precise summary of what the universe does to its objects. It builds them in environments of extraordinary density and violence, then disperses them across distances so large that any further connection to that origin becomes physically impossible. The deeper significance of S5, HVS1, is what it confirms about the galaxy's center. Kopasov's team called it the first clear demonstration of the Hill's mechanism in action at our own galactic core. Sagittarius A star has been flinging stars at escape velocity for billions of years. A small fraction of the galaxy's stellar population has always been in the process of leaving it. The galaxy we experience as a stable home is simultaneously a machine that continuously ejects some of its own members into permanent exile. S5, HVS1, traveling at 6 million kilometers per hour, will not reach the nearest neighboring galaxy for several billion years. It is a demonstration of cosmic violence rendered as a personal story, and it is not alone in what it foreshadows. But if one star can be ejected by the forces operating at our galaxy's center, an entire solar system can be ejected by the forces operating at a much larger scale. The Andromeda Galaxy is currently 2.537 million light-years from the Milky Way, approaching at approximately 110 kilometers per second. That closing speed has been measured independently by multiple instruments, including the Hubble Space Telescope's proper motion measurements and velocity data from spectroscopy. The approach is not uncertain. In approximately 4.5 billion years, the two galaxies will begin their first gravitational interaction. In approximately 6 billion years, they will have merged into a single elliptical galaxy that astronomers have nicknamed Milkomeda. Every star system in both galaxies will have experienced this event. Understanding what galaxy collision actually means requires abandoning the intuition the word implies. Galaxies are mostly empty space. The average distance between stars in the Milky Way is approximately 4 light-years. When two galaxies merge, the probability that any individual star physically impacts another is vanishingly small. The process is not a crash, but an interpenetration. Two vast gravitational fields overlapping, deforming each other's structure, generating tidal forces across hundreds of thousands of light-years, and gradually redistributing their combined stellar populations into new orbits over hundreds of millions of years. Gas clouds collide and compress, triggering intense episodes of star formation. Black holes at the centers of each galaxy spiral toward each other, eventually merging in an event that releases gravitational waves detectable across cosmic distances. The galaxies, as recognizable structures, are destroyed and replaced by something new. For any given star system, including potentially our own, the merger introduces a new gravitational landscape. Simulations, conducted by T.J. Cox and Avi Loeb at Harvard and published in the Astrophysical Journal, found that approximately 12% of stellar systems currently in the Milky Way will be ejected into intergalactic space during the merger process. The mechanism is the same one that launched S5, HVS1, amplified to galactic scale. Close gravitational encounters during the chaotic dynamics of the merger can accelerate individual star systems to escape velocity. 12% is not a small number. It represents billions of star systems sent into the void between galaxies, permanently separated from any galactic structure, their stars condemned to the same fate as the hypervelocity object discussed in the previous chapter. Recent James Webb Space Telescope observations of Andromeda's stellar halo have added detail to what is already a violent history. The halo, the diffuse envelope of stars surrounding the main disk, shows evidence of multiple past mergers and cannibalization events. Andromeda has already absorbed several smaller galaxies, each event leaving a trail of stellar streams and disrupted structures visible in the halo's composition. The galaxy approaching us has been far more active than previously understood, and some revised simulations now suggest the first gravitational interaction may begin as early as 3.5 billion years from now, rather than 4.5. The collision with Andromeda is itself the latest episode in a process that has been ongoing throughout both galaxies' histories. The Milky Way shows evidence of past merger events, most significantly, what researchers call the Gaia-Enceladus merger, estimated to have occurred between 1 and 3 billion years ago, in which the Milky Way absorbed a galaxy roughly 1/4 its current mass. The chemical and kinematic signatures of that ancient event are embedded in the populations of stars in our galaxy's halo, readable by modern instruments as a geological record of past violence. The structure of our own galaxy, its disk, its halo, its stellar populations at different heights above the plane, all bear the signatures of impacts. What the telescope is now revealing is that galaxy collisions are the mechanism by which galaxies grow, and in the early universe, that mechanism operated at a pace that makes our current situation look quiet by any comparison. In February of 2026, a team led by Webb at Texas A&M University announced the James Webb Space Telescope had detected 5 galaxies in the process of merging approximately 800 million years after the Big Bang. The observation had required some of the telescope's deepest exposures, targeting a region in the early universe where spectroscopic data confirmed the redshifts of all 5 objects as consistent with a single epoch. The merger was visible in the data directly: 5 distinct galaxies with overlapping stellar structures, deformed halos, and tidal features indicating active gravitational interaction. What made the observation significant beyond the spectacle of cosmic scale was the measured rate of star formation occurring inside this event. The combined system was producing approximately 250 new stars per year, each with the mass of a typical star. For context, the entire Milky Way in the present day produces between 1 and 3 new stars per year across its full extent. This ancient 5-way merger was generating stars at roughly 100 times the current galactic rate of our own galaxy, concentrated into an event occurring when the universe was barely 6% of its current age. Who stated directly that a merger involving so many galaxies was not expected to occur so early in cosmic history under any existing theoretical framework. The chemical signatures in this system compounded the surprise. Oxygen was detectable in the merger's light, the same indicator of multiple stellar generations that appeared in JWST 14.0 at 290 million years after the Big Bang. By 800 million years, its presence was less startling in absolute terms, but still significant in what it confirmed about the pace of the early universe's evolution. Stars had already formed, lived out full lifespans measured in millions of years, enriched their surroundings with the products of nuclear fusion, and contributed their mass to the next generation, all within a period shorter than the time that has elapsed since the mass extinction that ended the Cretaceous period on Earth. The observation did something else that complicates the picture of what calm and violent mean in cosmic terms. In the present-day universe, galaxy mergers occur, but the timescales between them are long and the frequency relatively low. The cosmic star formation rate peaked approximately 10 billion years ago, at a time sometimes called cosmic noon, when merger activity was roughly 10 times higher than today. The February 2026 observation pushed evidence of extreme merger-driven star formation back to 800 million years, well before cosmic noon, demonstrating that the violence of the early universe was a feature present essentially from the moment galaxies existed as discrete structures, not a later development that assembled over time. The distinction between the present and the past matters here because it reveals that our current epoch, the period in which the James Webb Space Telescope operates, in which our solar system exists, in which the Andromeda collision has not yet begun, is not a representative sample of the universe's history. It is a quiet interval in a long story whose dominant mode has been chaos. The structures that appear fixed and permanent from any human vantage point, galactic disks, stellar populations, planetary systems, are all the products of violence that has temporarily subsided. The calm is not the universe's natural state. What the data from both the early mergers and the modern simulations shared was a description of cosmic matter as something that builds structure by destroying smaller structures, assimilates by disruption, and organizes through episodes of catastrophic reorganization. The universe does not create through accumulation alone. It creates through collision. Everything the telescope has revealed about structure formation, from the impossibly massive early galaxies to the five-way merger at 800 million years, from the tidal streams in Andromeda's halo to the ejected hypervelocity stars, points toward a single underlying character of the cosmos. What exists now is the residue of violence. The timeline of cosmic violence runs from the Big Bang itself to the present moment without interruption. Within the first second after the Big Bang, the universe experienced inflation and exponential expansion so rapid that regions of space that had been in causal contact were separated to distances that light could not have crossed since. Temperatures fell from incomprehensible values to merely extreme ones. Protons and neutrons formed in the quark-gluon plasma. Light nuclei assembled in the first 3 minutes. Hundreds of thousands of years later, electrons combined with nuclei to form neutral atoms, releasing the photons that now reach us as the cosmic microwave background. Then darkness, the dark ages of the universe, lasting hundreds of millions of years, during which nothing visible existed anywhere. The first stars that ended those dark ages were objects unlike anything in the present universe. They formed from pure hydrogen and helium, uncontaminated by heavier elements, and accordingly they were massive, some theorized to have been hundreds of times the mass of a typical present-day star. Their lifespans were measured in millions of years. When they died, they either collapsed directly into black holes without exploding, swallowing their mass entirely, or they exploded as supernovae, more energetic than any in the modern universe, scattering oxygen, carbon, nitrogen, and heavier elements into the surrounding gas. The second generation of stars formed in gas, already enriched by those first deaths. The chemical clock started ticking from the first supernova. What the James Webb Space Telescope has shown is that the violence of those first eras was not a brief phase preceding stability. The observations spanning roughly 100 to 700 million years after the Big Bang describe a universe in which mergers, extreme star formation, black hole growth at super Eddington rates, and gravitational disruptions of forming galaxies were all occurring simultaneously and repeatedly. The pause between violent events was not long enough to allow the structures produced by each event to settle before the next one began. The universe in its first billion years was building order through chaos, each episode of disruption providing the conditions for the next phase of structure formation. The stars in the Milky Way today carry the chemical record of that violence in their compositions. The oxygen, carbon, iron, and calcium in every living organism on Earth were forged inside stars that died before our solar system existed, scattered by supernovae into the interstellar medium, swept up into the molecular cloud that eventually collapsed to form the star at the center of our solar system and the planets orbiting it. Every atom of every complex molecule in every living cell is the product of stellar violence across billions of years of cosmic history. Biology is chemistry built from physics that emerged from catastrophe. The stability that makes life possible, the relatively quiet current epoch, the near-circular orbit of Earth around a middle-aged star, the absence of nearby supernovae in recent geological time. All of this is a temporary condition in a universe whose default mode is the redistribution of matter through gravitational disruption. We exist during an interval of reduced violence, inheriting a planet built from the debris of ancient catastrophes, orbiting a star that will outlive us but not the universe. The violence is not over. It has merely paused at the local scale, and the objects that stand as the most concentrated evidence of that early chaos remain among the least understood things in the sky. The little red dots, catalogued by Jorrit Matthij's team at the Institute of Science and Technology, Austria, and colleagues, were introduced in earlier chapters as isolated anomalies, objects whose black hole masses violated the expected relationship with their host galaxies by factors of 300 or more, at a frequency 10 to 100 times what the models predicted. In the context of the cosmic violence documented since then, those anomalies take on a different character. The 341 objects in Matthij's catalogue appeared at redshifts between 4 and 8, corresponding to a period from roughly 600 million to 1.3 billion years after the Big Bang. They are compact and red, with spectral energy distributions shaped like the letter V, and their central black holes range from 1 million to 100 million times the mass of a typical star. In the present-day universe, those masses would represent a modest to moderately large central black hole. In the context of their host galaxies, the proportion is extraordinary. The black hole accounts for 30% or more of the total stellar mass in the same system, compared to the local universe average of approximately 0.1%. What the earlier analysis of cosmic violence illuminates is the mechanism that might produce this relationship. In the early universe, as documented through the JWST and CERS and Cosmos Web surveys, mergers were frequent and intense. Every merger event funnels enormous quantities of gas toward the centers of the colliding systems, feeding both rapid star formation and rapid black hole growth simultaneously. If those early mergers were as extreme as the February 2026 observation suggested, with star formation rates of 250 stellar masses per year, and chemical enrichment already advanced at 800 million years, then the conditions for runaway black hole growth would have been present across essentially the entire early universe as a matter of standard circumstance. The competing explanations for the little red dots, direct collapse black holes, super Eddington accretion, and primordial seeds all require unusual initial conditions. What the merger picture adds is a supply of those conditions that is not unusual at all. In a universe where galaxy mergers at 800 million years were already extreme, the environment needed to grow a black hole to 30% of its host galaxy's mass may not have been exotic. It may have been the standard experience of a galaxy in the early universe, not a rare exception requiring a special mechanism, but the predictable outcome of a cosmos that was running faster, hotter, and more chaotically than any model had anticipated. Spectroscopic follow-up of individual little red dots in 2025 showed that at least some objects previously classified in this category were producing far more ultraviolet light than expected from a pure black hole. Accretion disk, suggesting that the central engine and the surrounding stellar population were both contributing significantly to the observed spectrum. The boundaries between what counts as black hole light and what counts as starlight in these objects may not be as clean as the original characterization implied. Matthij maintained that his team was struggling to interpret the light from them. That struggle had become more specific, but it had not resolved. What these objects represent in the larger story the James Webb Space Telescope is telling is a universe that built its most extreme structures first. The largest black holes, the most massive galaxies, the most intense merger events, all appear earlier in cosmic history than any model predicted. The present-day universe is quieter, more diffuse, more spread out than the early universe was. If the little red dots seem impossible, it may be because the universe we observe nearby, the one used to calibrate our understanding of what is normal, is itself a diminished and cooled version of what came before. Something stranger awaits at larger scales. Something that does not merely challenge a parameter of the standard model, but questions the foundational assumption beneath all of them. Albert Einstein's general theory of relativity contains an assumption so foundational that it is rarely stated as an assumption. The cosmological principle holds that, at sufficiently large scales, the universe is homogeneous and isotropic, meaning that matter is distributed roughly uniformly in all directions, and that no region of the universe is fundamentally different from any other. This principle underlies every major equation in modern cosmos should average out, that no coherent structure should persist before dissolving into statistical uniformity. This prediction is not incidental to the model. It is a direct consequence of the physics describing how matter was distributed after the Big Bang and how gravity has had time to act on it since. In 2013, a team led by István Horváth at the National University of Public Service in Hungary, John Hakila at the College of Charleston, and Zsolt Bagoli detected a statistically significant clustering of gamma-ray bursts, spanning an angular extent that, when translated to a physical scale at the inferred distance of the objects, implied a structure of approximately 10 billion light-years in length and roughly 7.2 billion light-years in width. The finding was published and drew attention from specialists, but did not immediately enter broader cosmological discussion as a confirmed structural detection. In April of 2025, an expanded analysis revisited the original detection with a larger gamma-ray burst catalogue and found that the structure, which had been named the Hercules Corona Borealis Great Wall after the constellations it spans, was confirmed at increased statistical significance and appeared even larger than the initial estimate. It spans approximately 10% of the diameter of the entire observable universe. If the cosmological principle is correct, this object is 8 times too large to exist as a coherent structure. It should not be a single wall. The matter in it should have been distributed too uniformly by the dynamics of the early universe to remain coherent at this scale, and no physical mechanism within the standard model produces structures of this size. The Hercules Corona Borealis Great Wall is not the only large-scale anomaly. The Sloan Great Wall, discovered in 2003, spans approximately 1.37 billion light-years, just above the theoretical limit. The Boss Great Wall, identified in 2016, reaches approximately 1 billion light-years. But the Hercules Corona Borealis Great Wall is in a different category entirely. It exceeds the cosmological homogeneity limit by such a margin that accommodating it within the standard framework requires either revising the cosmological principle, which reorganizes the entire field, or finding an error in the detection method that no subsequent analysis has located. What the James Webb Space Telescope has added to this picture is confirmation from its deep survey data that the largest scales of structure formation are not following the predictions of the models. The impossibly massive early galaxies, the early black holes, the five-way merger at 800 million years, and the Hercules Corona Borealis Great Wall all point in the same direction. Something about the initial conditions of the universe, or about the physical processes that have operated since, differs from what the standard model described. The largest structure in the observable universe may be the most visible evidence that the model has boundaries we have not yet mapped, and the observable universe itself is the smallest portion of what actually exists. What the James Webb Space Telescope can see is constrained by physics that no engineering advancement can overcome. The observable universe has a finite boundary, not because space ends there, but because light has had only 13.8 billion years to reach us, and because space itself has been expanding throughout that time. When cosmologists describe the observable universe as 93 billion light-years in diameter, the number is larger than 13.8 billion light-years, because the regions we can observe were closer when they emitted the light we are now receiving, and have since expanded to greater distances. The edge of the observable universe is not a wall or a boundary of any kind. It is the surface beyond which information has not had time to reach us. Beyond that surface, the universe continues. Physics does not end at the edge of what we can observe. Space, matter, and the forces governing them persist past the horizon in a region that is, by definition, permanently inaccessible. Light emitted there is traveling toward us, but the expansion of space between its source and us is carrying that source away faster than the light can close the distance. That light will never arrive. Those regions are not distant, but reachable in principle. They are separated from us by a horizon that operates as a one-way membrane, and everything beyond it might as well be in a different universe for all observational purposes. How large is the region beyond? The question requires probabilistic methods because direct observation is impossible. Mihail Vardanyan at Oxford, Roberto Trotta at Imperial College London, and Joseph Silk at Johns Hopkins University, and the Institut d'Astrophysique de Paris applied Bayesian model averaging to the available cosmological data and published their analysis in 2011. Their conclusion: the total universe is at least 250 times larger than the observable portion. Alternative analyses using updated data have produced estimates ranging from roughly 400 times larger to the extreme case of a spatially flat universe, which the data marginally favors, in which the total extent would be infinite. 250 times larger means a minimum total diameter of approximately 23,000 billion light-years. If the observable universe's 93 billion light-year diameter were a single page in a book, the total universe would require a book at least 250 pages long. The analogy is misleading only in suggesting the total universe has edges like a book. If it is flat and infinite, the pages never end. What this implies is that the James Webb Space Telescope, with a mirror that captures nearly 6 times the light of its predecessor and detects objects 100 times fainter than what came before, is still seeing less than 1/250th of the actual universe at minimum. All of the impossibly massive early galaxies, all of the little red dots, all of the structures that challenge the cosmological principle, all of the dark matter filaments and supervoids and superclusters, everything documented in these chapters, exists entirely within a bubble that represents a small fraction of the total. In the regions beyond, physics presumably continues to operate, structures presumably exist, and galaxies presumably formed and evolved through all the same violent processes the telescope has documented. The significance is not merely about scale, it is about what we do not and cannot know. Every theoretical framework in cosmology has been built from data inside our observable horizon. Every model, every simulation, every constraint on the parameters of the standard cosmological framework draws from the same finite sample. Whether what we observe is representative of the total universe, whether the patterns and exceptions documented by the James Webb Space Telescope are typical or local, is a question that cannot be answered. The universe beyond the horizon will not answer it for us, and that horizon is itself already shrinking. The horizon discussed in the previous chapter is not static. Space continues expanding, and as it does, the boundary between the observable universe and the permanently inaccessible regions moves outward in ways that exclude more of the cosmos from our view with every passing second. Every second, more galaxies cross the cosmic event horizon, the surface beyond which their recession speed, due to dark energy, exceeds the speed of light, meaning their light will never reach us again regardless of how long we wait. This process is occurring right now, continuously, and its long-term consequences are more disorienting than any single number in this story. Within approximately 100 billion years, roughly 7 times the current age of the universe, all galaxies beyond our local group will have crossed the event horizon. The local group itself, bound together by mutual gravitational attraction that exceeds the local expansion rate, will remain. Everything else, every galaxy beyond the 2 or 3 dozen members of the local group, will have receded beyond the reach of any signal. The sky will still contain stars, billions of them, in the merged remnant of the Milky Way and Andromeda and their smaller companions. But external galaxies will be gone, and not merely faint. The photons they emit will never complete the journey. No future instrument, regardless of sophistication, will detect them. What this means for any civilization that might exist in that far future epoch was described precisely by Lawrence Krauss at Arizona State University and Robert Scherer at Vanderbilt University in a paper published in 2008. A civilization arising then would find, upon examining the sky, only the stars of the local group remnant. There would be no cosmic microwave background radiation visible, because it would have been stretched by expansion to wavelengths too long to detect with any physical instrument. There would be no distant galaxies showing redshift, because there would be no detectable galaxies outside the local group. There would be no evidence that the universe was ever smaller or hotter, no expansion to measure, no cosmic history legible in the sky. They would likely conclude, with full scientific rigor applied to the data available to them, that the universe consisted of a single stellar system of moderate size adrift in infinite static space. The entire conceptual history of cosmology, from Edwin Hubble's first measurements of galactic recession to the James Webb Space Telescope's catalogue of 500-million-year-old mergers, would be unavailable to them and unreconstructible from the evidence they could gather. The implication that follows is specific. We live in the only epoch in cosmic history when the universe's full past is legible. The cosmic microwave background is still detectable. Galaxies, at redshift 14, are still visible. The expansion is measurable, and its history deducible from surveys. 13.8 billion years of cosmic evolution, from the first quantum fluctuations through the first stars, through the violence of the early mergers, through the formation of our solar system, are all accessible from our current position in time. This particular window, this few billion years in the history of a universe that will last at minimum tens of billions more, is the only interval during which the whole picture is available to any observer anywhere. No civilization arising after this window closes will have the evidence needed to reconstruct what came before. What we know is something that will not always be knowable. The James Webb Space Telescope arrived at the beginning of the last era in which it is possible to read the universe's full history. And the history it is reading points toward three possible endings, each of them absolute, each of them certain in its totality, none of them yet distinguishable from the others. Three futures exist simultaneously in the current state of cosmological knowledge, and none can be eliminated by any measurement in hand. They do not represent competing speculations at the edge of the field. They are the three principal outcomes the data permits, each supported by different subsets of the evidence, each producing an ending of such totality that the word ending itself begins to seem insufficient. The first is heat death, sometimes called the Big Freeze, the outcome that remained the consensus prediction for approximately 2 decades following the discovery of accelerating expansion. Under this scenario, dark energy remains constant or weakens too slowly to matter. The universe expands forever. Galaxies beyond the local group vanish across the event horizon within 100 billion years. Over the following 100 trillion years, the remaining stars exhaust their fuel, cool, and go dark. The Milky Way Andromeda remnant becomes a cloud of cooling stellar corpses, white dwarfs radiating away their residual heat across billions of years. Protons, if the grand unified theories that predict their instability are correct, decay over timescales of roughly 10 rays to the power of 33 years. Black holes, stable against proton decay, persist longer, evaporating through Hawking radiation over timescales approaching 10 raised to the power of 100 years. After the last black hole, only the faintest possible traces of thermal energy remain, distributed across a volume of space so enormous that even the concept of temperature loses meaning. Maximum entropy. No further change is possible. This state persists forever, because forever is literally what remains. The second is the Big Rip, the outcome permitted by the phantom energy behavior. The dark energy spectroscopic instrument data suggested the universe passed through in its past. If dark energy's equation of state returns below -1, the repulsive force grows without limit as space expands. The critical timeline runs backward from the endpoint. Approximately 2 billion years before the final moment, galaxy clusters lose gravitational cohesion. 60 million years before the end, the Milky Way Andromeda remnant is destroyed. 3 months before the end, our planetary system is dismembered as the expanding repulsion overcomes the central star's gravity. 30 minutes before the final moment, Earth is pulled apart. In the last fractions of a second, individual atoms are torn apart as the force reaches the scale of nuclear bonds. The universe does not cool to silence. It accelerates through structure, then through chemistry, then through physics itself, until nothing bound exists anywhere. The third is the Big Crunch, revived by Henry Tye's September 2025 paper in the Journal of Cosmology and Astroparticle Physics. If the cosmological constant is effectively negative at the deepest level, gravity eventually wins the competition against expansion. The universe's expansion decelerates, halts, and reverses over the next 11 billion years. The sky, dark for hundreds of billions of years in the other scenarios, grows brighter as the shrinking volume concentrates the cosmic microwave background back into visible wavelengths. Structures that gravity assembled over the entire history of expansion are compressed back together. In the final stages, every structure dissolves into a fireball of decreasing scale, returning to the singularity from which the Big Bang emerged. Each of these endings is absolute. None leaves a remnant. None offers any physical mechanism by which information about what came before survives. The universe will end. The only uncertainty is in which particular form. And that uncertainty is not a small gap between nearly identical predictions. It is a three-way split between a cold eternity, a violent dismemberment, and a total collapse, governed by the behavior of a force that comprises 68% of everything, and that we cannot yet characterize with sufficient precision to choose between them. The James Webb Space Telescope began its science operations in mid-2022. By early 2026, 3.5 years into its primary mission, it had produced results that required revisions to the standard model of cosmic evolution, confirmed a fundamental crisis in the measured expansion rate of the universe, detected chemical signatures in the oldest confirmed galaxy that demanded multiple stellar generations, have lived and died before we expected the first ones to exist, and catalogued a population of black holes so massive and so early that no accepted physical mechanism could produce them. It had shown us the five-way merger of galaxies at 800 million years, the hypervelocity star fleeing the galactic center at 6 million kilometers per hour, and structures in the cosmic web that exceed the cosmological principle's maximum permitted size by a factor of 8. None of these results produced terror through spectacle. They produced something more precise: the specific discomfort of recognizing that the framework used to understand the universe, the framework that had passed every observational test put to it for 4 decades, was systematically wrong in ways that are not yet fully characterized. Every measurement that should have confirmed the model confirmed the crisis instead. Every anomaly that early observations flagged as possibly resolvable by better data became less resolvable as the data improved. The telescope did not show us that the universe is large. We already knew it was large. It showed us that we had been wrong about what the universe does, and we do not yet know how deeply that wrongness extends. This is the specific character of the terror the documentary title claims. Scale alone is not terrifying in the way the title means. Humans have known the distances to distant galaxies for a century. Edwin Hubble's measurements in the 1920s established that the Milky Way is one of billions of galaxies in an expanding universe. That knowledge has been absorbed. It has been printed in textbooks, narrated in planetarium programs, and described in every introductory astronomy course taught in the last 80 years. The distance to the edge of the observable universe is a familiar number. Familiarity is not terror. What the James Webb Space Telescope added was uncertainty at the foundation. The Hubble tension is not a measurement of how large the universe is. It is a measurement of how well we understand it, and the answer confirmed by the most precise telescope ever built is that we do not understand it well enough for both of our most precise measurements to be simultaneously correct. Dark energy comprises 68% of the total energy in the universe and may be changing, and we do not know what it is in the first place. The structures visible in the early universe appear at scales and densities the standard model does not produce. The cosmological principle, the assumption that the universe is homogeneous at large scales, faces a structure 10 billion light-years across that violates it by a factor of 8. The fate of the universe is genuinely uncertain between three endings, each of which terminates everything absolutely. The terror is not that the universe is large enough to make us feel small. The terror is that the universe is strange enough to make our understanding feel preliminary. We exist on a planet orbiting a middle-aged star in the outer regions of a galaxy that is itself a minor member of a supercluster flowing toward an attractor we cannot fully see, embedded in a void 6 times larger than the most extreme void previously known. In a universe whose expansion rate we cannot reconcile, whose dominant energy component we cannot identify, whose earliest history does not match our models, and whose ultimate fate is genuinely undetermined between 3 scenarios, each of which ends everything. Against that backdrop, our species has been here for perhaps 300,000 years. We have had instruments capable of measuring any of this for perhaps a century. We have had the specific instrument capable of reading the oldest light in the universe for 3.5 years. The window during which the universe's history is fully legible will close in 100 billion years, which sounds long until you consider that the universe has been here for 13.8 billion already and will persist for at minimum 33 billion more. We arrived late in the only era when the evidence was available, built the precise instrument needed to read it just before the window begins narrowing, and found, when we looked, that everything we thought we understood required revision. The James Webb Space Telescope did not reveal that the universe is terrifying because of how big it is. It revealed that the universe is terrifying because of how little, after everything, we have understood it. What we see now, in this brief window of comprehensibility, is enough to know that the questions we cannot yet answer are the ones that matter most, and that the instrument reading them will not be operational long enough to resolve them. The universe will continue operating by rules we have not fully identified, at scales we cannot fully observe, toward an ending we cannot yet determine. And we are here for only a fraction of the time it takes for any of that to unfold.